All right, welcome everyone. We're continuing the book club. This week we're talking about chapter 12, which is the chapter on Transformers. If you haven't heard of Transformers, you probably have been living under a rock. So it'll be interesting to kind of combine the perspective that's a little bit more mathematical that Simon Prince has in the book with just kind of the more practical stuff. We could spend hours talking about transformers and language models, so we'll kind of follow the book, and then I think maybe towards the end open things up to more like open-ended questions on stuff that's not really covered. I will try to include the intuition that he has, as well as some other things that I think are like kind of important intuitions around transformers. All right, so we are going to start with the professor's slides. He has provided these slides from an undergraduate course that he taught. The book is newer than the course, and also the course kind of ended right about here. So I've had to augment this week's slides, and then as we continue the rest of the book, we're going to have to independently, there are no more slides for us to follow from his course. All right, so this is the outline. Sorry, this is not the outline. So natural language processing was the motivation for the original transformer. There's a lot of different tasks that are involved in NLP. So if you've heard about people doing translation from one language to another, so French to German, question answering, summarizing, you can see generation, all of these things, motivating, and so lots of other things. We're not in this book going to actually talk about a lot of the historical technologies. So in particular, we're not really going to talk about RNNs. I'm going to have a comment at the end about recurrent neural nets, but this is really just about the current technology, which is transformers. All right, so first let's talk about the motivation a little bit, okay? So you've got a neural network, you want to process text. So here's some sample text, the restaurant, blah, 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 blah. What are some of the problems with trying to understand this? Well, you might map each word to some kind of vector, some kind of numeric thing so that you can process it. But like, okay, we've got this sequence now of multiple words, and I think, is it on this slide? So if you map each word to, say, a length 50 vector, 50 floating point numbers, as soon as you're talking about like whatever, a page of text, what is it, 500 words or something like that, you're now talking about like 500 times 50. So for just like a traditional tabular data or fully connected neural network, you know, right? You're already in the tens of thousands of parameters. Things are getting big, and this isn't even talking now about like large text, long text, or whatever. So naively, what you can imagine, showing here on this slide, the first figure in the book is like, hey, let's just build a fully connected neural network and connect it to like all the parameters or whatever, right? And so this is where very quickly what we're talking about is getting into the tens or hundred thousands of parameters for just doing like some simple text and having a simple embedding for each one. The other thing that's really kind of weird about text is, let's say you're processing reviews that someone did for your product. Well, some reviews are short and some reviews are long, and a fully connected neural network like a vanilla one doesn't really know how to deal with this. I mean, you can say, what am I going to put in zeros? Am I going to put in negative ones if it's shorter? Like, but you do have to figure that out. So the idea that people were looking at is, let's build some model that sort of understands the idea of a sequence of words, and the number of parameters is based on the complexity of our word space, but the number of parameters doesn't grow with the length of our string, with the number of words. And so that's where different technologies were explored, including the RNNs that we're not really going to talk about, okay? So now you've decided, I want to do that. I also have this other thing that I want is in this sentence, in this review, it says the restaurant, blah, 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 their ambiance. Well, what is their talking about? There is referring to the restaurant. If you're going to build a good language model, you want it to be able to do these kinds of things, to be able to say there must be referring to restaurant. there's lots of other things you need to do, but this is like a pretty concrete example. When you have pronouns, if it's a good language model, it's going to have to understand the relationship between the antecedent. What the heck is that pronoun talking about? So we've got those motivations. And so for a good model, 2 bullets at the bottom, there must be a connection between the words, and the strength of the connections will depend on the words themselves. We're not going to be able just to, like for computer vision, have pre-built connections. In computer vision with CNNs, we said each pixel is going to look at, let's say, the 8 neighbors all around it. We don't get to do that here. So the technology that we're going to talk about here is this idea of dot product self-attention. So first of all, let's sort of define this a little bit more rigorously. Okay, so our text, we have n inputs, so n words. I'm going to mostly say words. I might say tokens at some point. For those of you who know NLP, it's no longer a one-to-one correspondence, but the mental model is the same, whether you think of them as true words or as just some other word token that could be smaller than a word or bigger than a word or whatever. Conceptually, it doesn't really change the mental model. All right. So we're going to map each of these input words, input tokens, to a vector of length d. Okay. So let's say d is 512 or something like that. That's a fair number of inputs. And if it's of length n, then the kind of model that we're going to talk about, again, this is after many iterations of other things that didn't work, is a model that inputs n words and it's going to output n values. So however long your input is, we're going to get an output for every single one of those. And then in standard neural network notation, basically your inputs are your x's. We're going to have n of them. So this is x is technically going to be an n by d matrix. We're going to have our weights that in this book, the author uses omega to describe the weights. And then we're also going to have biases, which oftentimes for notational simplicity, people don't show them explicitly. But so we're going to add the biases. And that's going to equal our outputs, v, which will also be length n. So that's the mathematical notation. And how we're going to do this is we're going to have some function a, which at this point we have not defined. Okay. A is going to say, I have my input words x, all n of them, and I'm going to have some subset of those words m. Again, not necessarily explained at this point, but basically from this, I'm going to calculate the strength of relationship between the n words and the m words. Okay, and I'm going to use this to then weight the values that came from the first equation. Okay, so if those of you who know like the transformer, like we're sort of backing our way into this, but if you don't know this, the whole idea is that for each word, I want to calculate a value, and then the second equation says I am going to have some unknown, at this point, unknown function a that's going to tell me how much should I include, how much should I weight each of those contributions from the different positions, okay? So eventually we'll see that a is going to be an attention function, which is why they use the letter a. And then SA is our final output. This is self-attention. And the reason why it's called self-attention is because we're using the same x's as both of the inputs for attention. Okay, they're not necessarily completely identical because you see there's an N and an M here. Okay, and actually, as I'm reading over this notation, I think I may have misspoken. It might be referring to X sub n as just the nth item. So there's big N total of them, but X sub n is just one of them. So it's not the matrix I said. It's just length 512. And so this is saying comparing any pair N and M of things. So sorry about that. Eventually, when you combine them all together, then you'll get a big N length thing. But this is the function for calculating any single one of them. So for our third output, we're going to compare the third inputs to every other input with this attention function, and we're going to sum up all the values from those. All right, so that's fine as a mental model, but how are we actually going to calculate this mystery function A, right? So the key thing is that this top function looks like a perfectly normal neural network, okay? The output is just based on the inputs and some weights and biases. What we're doing is we're saying we're having kind of a neural network model here, and it's going to create the weights for those outputs V's. So there's an older term in machine learning called a hypernetwork, whereas the idea is you build a small neural network that sets the weights on a different neural network. So that's the idea of the hyper, okay? And so for people who are familiar with that concept, this attention really is a hyper network idea, that you have one part of the network telling you how strongly or weakly to weigh the outputs of a different neural network. So another way you can think about this same thing that we talked about is routing. So let's use a very small example where big N is just 3. We only have 3 inputs, okay? And so what we said is the self-attention is going to compare for the first token for X1, it's going to compare it one by one with each of the other ones. Our M is going to be 1, then our M is going to be 2, and then our M is going to be 3, okay? So this, again, at this point, it's just a mystery function A is going to, let's say, I'm going to weight 0.1, the value from X1 with itself. I'm going to weight 0.3, X1 weighted with 0.2. I'm going to weight 0.6, the value coming from X3. We haven't said what the values mean. We haven't said how we're going to calculate this. But if these numbers add up to 1, you can think of them sort of like probabilities. But essentially what we're saying is we're always calculating a value for every input token. What the A function is going to do is decide how much. So in this case, you say it's mostly pulling from number 3, it's pulling from number 2 a little bit, and it's mostly ignoring number 1. We're going to do this at every position. So for token 2, we're also going to get the contributions from every position, and they may be weighted differently. So in this case, you can see the first one's weighted 1/2. And for the third token position, it's again a completely different A function, a different attention function that does the weighting. So this is our concept of how we're going to build outputs based on our inputs and based on some special function A that decides how to route or combine the different values we get from our inputs. Now we need to flesh out those details. So what we're going to do is we're going to have this A function. Remember, it's using one input N, and it's comparing it one by one to each of the other inputs M. And so we're going to have this idea of a query and a key. I haven't particularly found the idea of like dictionaries, query lookups, query keys to be a super great, helpful mental model. For some people, if that works, great. But the whole idea is basically for every input, we're going to calculate 2 separate things. We're going to calculate the query for when in that equation, it's the first parameter, it's the X sub M. We're going to calculate a separate thing when it's the second parameter, it's the X sub M, okay? And then what we're going to wind up doing is we're going to say we want a similarity function that says if the query for token N and the key for token M are very similar, we want to give this a very high weight in our special function A. And if they're very dissimilar, we want to have a very low weight. You can just use any similarity function. If you want the numbers to add up to 1, you need a scaling function. And so we're just going to use the softmax function. You could do linear scaling. The softmax function with an exponent of 1 more strongly weights things that are a little bit higher. So if you had like a 0.4 and a 0.3, they're pretty close together. Once you do e to the 0.4 versus e to the 0.3, they're now farther apart. And so it is a weighting function that tilts the scale towards the bigger values, okay? You could have other weighting functions that did the opposite, that tended to make things much more equal. In this case, experimentally, softmax works pretty well in order to say we're going to have a range of values and we're going to put a lot of emphasis on whichever value is the biggest. Any questions? Yes, please. Say that again? Yes, so the question is, do the tokens have to be the same thing? So in this case, yes. Again, this was invented for the language case. And so what you're doing is you're comparing every word to all the other words. And so your only input is the words. And so the words have, yes. Every word gets mapped to the same length vector, even if the word in the native language, English or whatever, might be different numbers of characters or whatever. All right. And so ultimately, what we're going to do is we're going to suggest that this similarity function be the dot product. Okay. So we have a length 512 vector. We for the key, a length 512 vector for the query. And so we do the key transpose times the query. That will give us a single value. And on the next slide, we have a little bit of intuition around this. Hold on one sec. Question, what is meant by tokenization? We're actually going to get to that, but for now, super simplistically, you can think of just tokens and words as being the same. Early models, that was always true. That's not true anymore. But for your mental model, it's close enough that for now, it's good enough. Okay, so we're not really going to go into the math that much, but the idea here is we're going to use the dot products. And so, hey, if you guys remember your linear algebra, if you've seen this in other machine learning contexts, okay, two vectors that are very close to each other. If the angle is small, if it's close to 0, then their cosine of that is going to be close to 1. If they're orthogonal, it's going to be close to 0. And if they're pointing in opposite directions, you're going to get a value close to -1. So you have sort of 3 potential concepts of similarity. They're pointing in the same direction. They're very similar. Okay. If they're pointing in opposite directions, it's like anti-similar. I don't know if that's a word, but basically it's the same concept, but in opposite directions. And if it's a different concept, if you have dog and the color red, then you might get a value that's close to 0 because they just don't really have much relationship with each other. Whereas you would think that maybe like dog and wolf would have a value very close to 1. I don't really know what would be a -1 for the analogy I just made up on the spot. You know, dogs and cats maybe in one context, you know, but -1 maybe doesn't always apply for every situation. Okay, so that's all we're going to do. Talk about the math. We're not going to go really into the math. But we've sort of declared this is our similarity function. All right. Trying to remember what's on this slide here. So recapping our motivation. So we wanted something that processes text, that the number of weights is based on the word embedding, but not based on the number of words. And we want something that can figure out a way to decide which words are related to each other, okay? And so we're saying we've kind of met those criteria of what was desired for this, okay? Because we're going to have a very small neural network. It's really just going to be one weight matrix that turns each word into a query. We're going to have one small matrix that turns each word into a key. We're going to have the value thing, which again is just a single layer. It's just a square matrix. And so here you see these weights. The weights sub k is the keys. The weight sub q is the queries. The weight sub b is the values. Okay. And the function a, we've now said, is the dot product. It's hardwired. That's part of our architecture. That's not a decision you get to make. Okay. And so there's now this connection between all the words, which is formed by the similarity between the queries and keys, and the strength of them will depend on the words. It's not just a predetermined, like with the CNN, where my 8 neighbors have strong connections and everybody else has weak connections. All right. What we haven't said is is there any way to train this thing to have queries and keys that are actually helpful and to have values that are useful, but it at least meets the criteria of what we said we wanted in terms of a language model? Any questions? Please. I'm not sure if I heard you. So like, why do we want a model that, yeah, yeah. Yeah, so we want a model that doesn't increase with input length for two reasons. One, just because if you have 1,000 words on something like a 2-page thing, then that means you need 1,000 times more parameters, and that's not very cool. But then the other thing is, it's just awkward to build a model that can take an input that's this movie sucks, 3 words, but also take in 500 words, pros. Well, the acting was good, the cinematography was good, the sound was cons, and it's like, how do you build a model that's equally good at a 3-word review and a 500-word review? Yeah. Any other questions? There's a question online: is the model at this point linear? Are there any non-linearities? So it turns out that this dot product and softmax that we do is already nonlinear. We're going to add more nonlinearities to this model, which if you guys sort of know, like you have to add nonlinearities if you're trying to increase the complexity. For those who've been following the book club, we started with just single layer neural networks. We went to deep neural networks. And so there was the idea that you had piecewise linear functions. And so the nonlinearities like ReLU are what allowed us to create more pieces. Okay, so these are not necessarily piecewise linear, but we want more complexity in order to have the representational capacity. We want basically our model to be able to fit any curve, okay? Not just super simple lines or close to lines or whatever. So you want that power. What we still haven't said though is just because you have some theoretical representational power does not mean you can train it to fit what you actually want, right? That proof in the pudding will come later. Okay, so we showed this kind of, and I kind of jumped the gun a little bit when I was thinking about things as matrices, but we were thinking of this kind of just one word at a time. Okay, so for word number 3, I'm going to calculate attention to all the other words 1 through n. I'm going to sum up the values. Turns out that for computational efficiency, you don't need to do this one at a time. You can actually calculate the attentions for all of the queries and keys all at once with one giant set of matrix multiplies. It's not really required for you guys to understand this, but just know that if you are looking at code for a model, what you're going to see is that the input x is now not going to be capital N separate length 512 vectors, but it's going to be a whatever the length of your string is, n by 512 matrix. Okay, and you can appropriately size your value, query, and key matrices as well, so that they're not working individually, but they're all just sort of concatenated, so that when you do a matrix multiply, magically you get the exact same numbers if you did it one at a time, but you're just doing it in one big thing. Yes. The question is X usually the transpose? Is it D by N or N by D, whatever? This is something that confuses me all the time. I don't know the answer. What I can tell you is that sometimes you will see the weights left multiplied by X, and sometimes you'll see the weights right multiplied by X. And so like I can tell you that like when I did a previous meetup and I was playing around and I was hand coding the weights in order to make the model have a certain kind of attention pattern, right? I wanted like the word whatever he to always pay attention to the word boy or whatever. I cannot tell you how many times I'm like, is this the right weights? Let me just transpose it and see if that fixes the problem. Like 1,000 times. Okay. I'm sure like Andre Karpathy would have a much better, great answer, but for me, it's just like
coded it as N by D. Why it has.
But I'm just saying. So there may be some implementation that, in theory, if you transpose absolutely everything, it'll always work, right? But there is a convention, and I don't really know exactly who uses. But what's important is that you should know it is N by D or D by N, one of those two. And depending on your implementation, you need to either left multiply or right multiply, and everything will work out. All right. So yeah, so you can do this in matrix form, and then with modern GPUs, they do a lot of matrix multiplies when they're doing all the video game stuff. You know, the ray tracing and the what is that? Where you apply patterns to surfaces and whatever. So they already had a lot of this matrix multiply hardware built in, and so when machine learning came along and said we need to do a lot of matrix multiplies, then NVIDIA was like, hey, I got just the right thing for you. All right, and so here is a diagram where you can see your input comes in, and you have N by D, D by N. You've got the query calculation, the key calculation, the value calculation. The queries and keys, these get dotted in this portion of the branch, and what you get are attention weights. And so the attention weights are always a square matrix, because if you have n tokens on your input, each gets compared to every other one. It has to be a square matrix. And then you have your values, and the attention is weighting how much contribution from each of the values, and so you multiply those two together also. Is that a question? Yeah. So the question is going back to the text example that we saw about a review about a restaurant. We had the word there, and you have to know that that refers to the word restaurant. So algorithmically, it's really complex to say what does the language model have to do, okay? But what we would say is the answer is yes, at some point, the model needs to be able to do a calculation to say, I want information about restaurant to be available when we're processing the word there. Okay. In a different sentence, there would be referring to whatever, a train, not a restaurant. And so you need different information to be available at that time. What's unclear, even if you like study language models, is well, how exactly are you getting the information restaurant into the position where the word there is? Okay. But what's very clear is that you see these attention patterns, and what's happening is when there's strong attention, the values are getting copied from the attendee, whatever the token that's being attended to, into the current word position. What's not clear is how exactly the model decides what the values are that it should copy, okay? But simplistically, you can think of it as it's basically copying the information that the previous word was restaurant into the current position, so that the rest of the sentence, when it sees the word there, can almost treat it as if the word restaurant was there instead of the word there was there. So the question is, I said the word copy. So we haven't gotten to the architecture yet, but literally in a model like GPT-3, what attention does is it looks left at all of the old previous words that have appeared, and it copies information. Again, we're looking at all the words, so it's a weighted thing, but if all the attention's on one word, it is copying the value. So this particular V calculation on the bottom path, sorry, I accidentally clicked. So we say, here's the output. What's going on? That output is getting written to the current token position. Okay, so we'll see in the architecture, but when we calculate the attention, let's just say for giggles that the attention between this word there and the word restaurant is 1, and the attention everywhere else is 0. Then basically this value that's calculated for the word restaurant is going to get written into the position of the token there. So that's literally what is happening in the model. And again, it's not even just you asking. It's like, we've been trying. We still don't know exactly how it knows what to copy and what information to put there, but it is some version of the restaurant-ness gets copied into where there is, so that when you're saying what's the next word that should be, it knows that we're talking about a restaurant. And then it also still is going to retain some information because there's they and there's there, and so this is the possessive, it's not the whatever. So it's not losing all the information, but basically it has to know you're talking about a restaurant, not a train. Yeah, so it's part of the software, it's part of the model. When I say the word copy, you'll see later on, I literally mean copy. Yeah.
I just realized that the operation B times softmax and take transpose Q is happening like that linear. If you view the attention matrix as a linear transformation, it has rank n, right? So the output matrix, like all of this operation, like all these operations are happening in a subspace that's much lower than D because you're working in a linear subspace that's rank n more than n, right? When you're taking linear combinations of tokens, unless you have a number of tokens greater than D.
So to paraphrase, the question is about this attention matrix is rank n, and if n is smaller than D, so like if you embed your words into length 512 vectors, but your review only had 10 words, this is only 10 by 10. This is much lower rank. So I would say that the way I think about it is this n by n is talking about the weighting of the different V matrices. So for word number 10, if it's predicting the 11th word, okay, word number 10 is going to get contributions from itself and the previous 9 words. And so it's going to have 10 rank D matrices that it is summing, 10 rank D vectors or whatever, that it is summing with some level of weighting. And so you're not losing any rank because the things you're summing are all rank D.
All rank n.
And they're rank D.
I mean, if you have a vector, it can't have a rank. It's just a single vector in a D-dimensional.
Sorry. It's a length D vector, and if you have n vectors, you only need a rank n matrix to decide how much to weight them.
But what I'm saying is, like, okay, say you have your rank. I mean, we can talk about this later, but what I'm saying is you have n vectors, right? And you're taking linear combinations of those n vectors, and you're living in a space of dimension D. Then the rank, you only have access to an n-dimensional linear subspace of the rank of the entire rank D dimension. So when you take linear combinations of those n vectors, you're only going to be able to, you can't move them into like outside of the linear subspace that those 10 vectors live.
So the question again is around if you have n vectors and n is smaller than D, are you somehow restricted to an n-dimensional subspace? And what I would say, and we can take it offline if you have more questions. I would say the answer is no, because the n's are your scalars for weighting your vectors in RD. So it's not in any way reducing your dimensionality. It's just combinations of full length D-dimensional vectors.
Yeah.
Cool. All right, let me just check. There's a bunch of messages in the chat. All right, so some stuff about words and meaning. All right, if there's something else you guys want me to answer, you can repeat it, but I don't see anything that's necessarily a question for me to answer in the chat. Okay, so this I thought was an interesting slide. I like some of the intuition here. Okay, so this slide shows pictorially how the values are calculated if you have 3 input tokens. Okay, and so you have a certain matrix that for token 1 is being multiplied by the 512 floats for token 1. And then you're also multiplying by values for token 2, and then so for token 3. And so there's no interaction in the calculation of the values between different tokens. And so I think this is to sort of contrast what a fully connected network that connected the 3 tokens to our current value weights. Okay, so this is where, again, we said we wanted this model that didn't scale the number of weights with the length of your system. Okay, and so what you see is we're just repeating this same set of weights 3 times. There's really only one set of value weights. They're just shared and repeated. Whereas if we had the naive fully connected network, then this would be 3 times 512. This would be approximately 1,500 in length, and you would need that many weights. Okay, so this gives you a sense for how we're moving towards our goal of having fewer weights, not having weights scale with the length. Okay, and then obviously if it's more than 3 tokens, then you still are only having this small number of weights over here, and they're repeated on the diagonal, but it's not even growing linearly. It is constant. So whether this gets to length 10,000 words, it's still going to be the same number of value weights. It's not going to grow at all. We can do the same thing with the queries and keys. Okay, the number of queries and key weights does not grow as the string gets longer. This one's a little bit harder to see the pattern, but basically what happens is queries and keys are looking across tokens, but because of the fixed number of weights, it is this pattern. And so you can see everywhere where there's a white square, there's not a brand new weight. But in the fully connected network, we would have needed weights for all of those. So I honestly didn't even spend the time to try and verify that this slide is exactly right or whatever, but I just, the concept is clearly there that each of these lighter and darker shades of brown represents one of the weights in this little 3x3, matrix. And it's just showing you that you're reusing those weights, okay? And that something fully connected would have needed way more weights, okay? So just visually kind of reiterating the whole business about how we have a fixed number of weights based on the size of our word vector dimensionality. It does not grow based on the length of the string. All right, so if we're gonna actually do work with this model that we've proposed so far, where we do a query, a key, we do a dot product, and we have these values. If you look closely, one thing you'll notice is that the dot product does not care where the words are. So we talked about the word there and the word restaurant. Any place the word restaurant appears is going to have the same key. And any place where the word there appears is going to have the same query. So it doesn't really matter where they are. And then you can see an example here. The man ate the fish and the fish ate the man are 2 very different sentences, but they contain the exact same words. So in order to really make this work, we're not actually just passing the words in. We're passing the words plus some position information that says this was the first word, this was the second word, this is whatever. And so then the next couple slides are going to talk a little bit about how they do it. It's not super critical that I don't think, that how this is done. But the idea is that now it's not really the man ate the fish, but first word the, second word man, third word ate, fourth word the, fifth word fish. Now these 2 thes are not the same because this one is a first word the and this is a fourth word the. So now if the model's smart enough, it knows what to do with that information that tells it, where things are. So if you look at like sort of the original model, they said, here's this pattern, which I don't know if you can make sense of it, but basically we use like sines and cosines, and you have different periods. So you have really long periods that will be able to tell you like where something is across the entire length of things, and then you have shorter ones that can tell you like. But if you had like an max input length of say 4,000, and you just had one sine wave, one sine and cosine that told you the whole thing, it'd be very difficult to tell words that are two words apart because their sine and cosine are going to be very similar to each other. So that's why you need kind of a mix. You need some big ones that tell you long range distance, but you want some higher frequency ones that have better resolution for when you want to know if something is only like two words apart or whatever. If you get this, great. If you don't get it, it's not super important. Ultimately, I don't know if it's, I don't know how strongly I can say most, but I think most models now, the position codings are just trained along with everything else. They're not handcrafted. So at the end of the day, we don't really know if the weights look like this or whatever. But people have done enough studies on models to see that there's always something that has low frequency patterns for long range distance measurement and something that has high frequency patterns for short range distance measurement. And I can't remember if there's slides or not, but you can have absolute positions and you can have relative positions. And at the end of the day, as long as you have both high and low frequency, the model seems to be able to do what it wants to do to understand where words are relative to each other. And so mathematically, what this means is if you take this position information and let's say it's an actual like vector or whatever, you just basically add it. So in the system, the original equation says self-attention equals the values times the softmax of keys dot queries. Now they're saying nope. Instead of the actual values, it's values plus position information times softmax of keys plus position and queries plus position information. I don't think we're really going to do more with these equations, just kind of showing you that formally there's more information going in than just the tokens. All right, so we've got the building blocks. Now let's talk about the actual transformer, which has a little bit more to it than just this self-attention mechanism. First thing is there's a scaling factor, not super duper important, but we take our equation and we're going to change it by dividing by the square root of d. The next thing is you'll hear about this concept of multi-headed self-attention. I'll just simply say that, like, imagine your vectors are length 512. You can calculate one query based on all 512, one key based on all 512. You're putting all of your special attention calculation on this one comparison. Well, you could divide it into two halves that are each 256. And so you could compare the first halves of the queries and you could separately compare the second halves of the queries. And now you could have two different attention patterns. Okay. And so most of the language models you look at now, Llama, Mistral, whatever, I don't know the exact values, but typically it's going to be somewhere around like 12 to 20 attention heads where they're taking this token and instead of calculating just one attention pattern, I'm sure that would work. You might just require more layers in order to be able to have more complex calculations, right? But instead of having a whole bunch of layers, what you can do is you can just divide up the queries and keys into this, 12, 20-ish range, and you can in parallel calculate a whole bunch of different patterns. And what people have found is that works pretty well. The conventional wisdom is you divide them up smaller in a way that the computation isn't any more expensive than if you just did one big 512 attention calculation. Mathematically, there's no reason why you have to do that, but that just has been the convention. There is a very fast implementation with matrices on GPUs. So it's kind of like, if it ain't broke, don't fix it. People just do that. And I haven't really seen any research on what if we use like different ways of breaking it up. It's just like, yeah, good enough. Let's just move on. So then this diagram, if it works for you, great. This diagram is kind of rotated 90 degrees from the way I'm used to seeing things. So usually I see words going left to right across either the top or the bottom. And in this case, the words, the inputs are on the left, okay? And the sequence is vertical. So the fish lived in the is the first 5 words coming in. And so we're saying each word gets converted to a vector. There's a self-attention calculation that compares each word to the others. The value's not really shown here, but these attention weights get multiplied by values. And so you get these tokens here. There's another component. There's just a fully connected one hidden layer network that's also part of the transformer. And if you combine the two yellow boxes, the attention layer and the feed forward layer, then that's what today everybody calls a transformer. This is, sorry, this box with the yellow boxes is the diagram that was in the slides. In the book, there's a slightly different diagram. He sort of updated it, but it's really the same concept. You have your input, which is N by D. You have multi-headed self-attention. The value is not really shown. There are normalization layers. So he's just adding, that's not really doing computation, but it's doing scaling. So he's explicitly showing there are normalization layers. This is the feed forward network. And then another detail is that there's actually a residual connection around each of these two components, the attention and the feed forward. So it's not just the value that you calculate from attention, but rather it is added to just the identity, just to what the original values were beforehand. There was a full chapter on residual connections in the book. There weren't really slides that went with it, so we kind of didn't spend a lot of time on it. Residual connections turn out to be super important for the trainability and stability of neural networks. I don't know if you mental model wise need to know a lot about the residual connection. There's one way in which I'll talk about later where I think it's important for LLMs to think about the residual stream. But otherwise, residual connections, just know that they're there so that if you see a diagram, you're not confused by it. But it's not doing any math. It's just the same value, getting passed through. So then I also wanted to show most of the time what you're going to see is this picture, which is from the original Attention is All You Need paper. Okay. I'll be doing a little bit more with this diagram. The hard thing about this diagram is that if you look on the lower left, it says n times, and on the right, it says n times. So it's sort of like you have to repeat this thing. What it also doesn't show is that this entire thing you have to repeat for every token position. So there's a lot of mental abstraction you need to do to say, what actually does it look like if I build something out of this? So I have a slide later that I use that I did a lot of copy and pasting so that you can see what it looks like to have L layers and N tokens, as opposed to just having to mentally kind of like say, well, what's going on there? All right, a couple other things if you're doing NLP to know about. So there was a question earlier about tokenization. So now we're finally going to get to this. Okay. Early versions of NLP, mostly one input was one word. Sometimes you would hear people talk about like stems and things like that. So that basically if you had whatever, like throw, throws, no, it's an irregular verb. Walk, walks, walking, walked. They're kind of all forms of the word walk, okay? And so you might do something with that. You got to deal with these different kinds of edge cases. So it's kind of a separate topic, but what you need to know though is that if you're going to build a language model, you do have to have tokenization, okay? You have to decide what are your units of input, and then the next step you're going to do is you're going to have to convert every input into a vector of length, whatever you choose, 512, 8,000, whatever, okay? And so one of the big problems in tokenization is that if you start training your model on a lot of text, your vocabulary just keeps getting bigger and bigger and bigger and bigger. Oh, now you included some legal text. Now there's all these weird things that appear in law books. Oh, now you're including some medical text. Now there's all these medical terms. And it's very difficult to get good coverage of all the vocabulary, and it's very difficult to. And then what do you do if you're trying to use your model and all of a sudden it's something about cars and there's a word that never appeared anywhere in all of your training data. Now it's just this complete unknown, okay? So in the past, people did that. They literally had a token that was called unknown, but you can imagine that the model's not going to be very smart about dealing with when it sees the unknown word. So pretty much the standard today is people do this thing called subword tokenization, where at a minimum, so for English, you would have all 26 letters available to you as tokens. And so if you see a word that you've never seen before, worst case, you can just spell it out and have one token for each letter. So you'll never need an unknown token. Okay, there will always, at a minimum, be some way you can represent it. Now, whether that's a helpful representation or not, it's a mixed bag. Okay, if you're if you have text and it's from some brand new TV show and the TV show has made up terms, you know, maybe the model's not going to be able to guess very well. But if there's a medical term and it has like certain roots in it, then it might actually pick out some of the meaning. Because if it says oh God, I don't know, I'm not going to try. I was going to try, but it just, it might be able to see like, oh, this is kind of a root that means inflammation, and this is a root that means cancer, this is a root that means whatever, and so it might be able to, kind of glean some of the meaning out of it. So there's an example here. It's not super, super important, but there's this nursery rhyme. The top of it's cut off on my screen, but um, basically it's the sailor, whatever, to see what he could see, but all that he could see, was the bottom of the deep blue sea. And I'll just very quickly go through this, but so if you're doing subword tokenization, the original byte pair encoding, if you want to like look it up on Wikipedia, first you just look at all the characters and you say, okay, this is how often each character appears. Let me find the pair of consecutive characters that appears the most. And it's going to turn out that it's SE, okay? And so in the next step, you're going to create a new vocabulary word, which is SE. And then you repeat this process, and you're treating SE now as atomic. And you're going to say, what is the most common pair of consecutive things? And it turns out it's, I don't, E space, okay? And then you repeat this process. If you repeat it like 26 times or whatever, then you get the word CSEE, you get the word CSEA. The letter E appears by itself fairly often. And remember, we now no longer count any of the E's that are part of SEE or SCA because those are now their new atomic things. So you repeat this process and basically you get to build up your vocabulary based on the most frequent pieces. So if you're curious, this byte pair encoding actually came from people who worked on compression. Okay. And you can continue this process. And if you did this forever, eventually you would get to the point where all you would have is complete words. You'd have no more letters by themselves left anymore. Okay. So what does this process look like if you do it? Apologize, my screen's cut off a little bit, but left to right is as this process goes longer and longer. Initially, when you run this process, your vocabulary size grows because initially we had all the letters and now we also added SE. So we basically added one more word to our vocabulary. And initially what's going to happen is you're going to keep doing this. But eventually what's going to happen is when you make a bigger thing, the smaller thing is going to go away. And so you see there's this pattern where initially the vocabulary grows, then it goes up and down, stays relatively stable. And eventually if you run it long enough, the vocabulary size will start to shrink. So basically, based on your compute budget, when you're building a language model, you decide upfront what I want my vocabulary size to be, and so you run this process however long until you hit your vocabulary size limit. The different tokenizations you see out there have to do with some of them only allow up to whole words, so you can have a space at the end of a token, but you can't have anything after that. So that was sort of the original, I think it was called like word piece tokenization. A lot of people now use sentence piece where you're allowed to have spaces in the middle of a token. So if you have two word combinations that are super, super common, I don't know, White House or whatever, machine learning, super common, right? You could theoretically have a single token that's multiple words and allows spaces. So that's the differences when you see different models have different tokenizers. It really has to do with what languages, what text were they trained on, and what do they allow inside of things, and how do you handle punctuation, and do you do only lowercase or do you do mixed case? It's all those kinds of things kind of decide your tokenization. So not super important to know exactly how they build it, but just if you know that that's something that they do, then once you've decided all of your tokens, each token gets converted to a vector of length d. I've been saying 512 a lot in this meeting. Okay. And so then basically the matrix that that sort of converts it to your vocabulary, it's basically just this, it's a lookup table. It's this giant one hot thing that basically says if your vocabulary is 30,000 and your embedding size is 512, it's a 30,000 by 512 length matrix. And every word just picks out one column from this matrix. So it is technically a matrix multiply, but it's not a particularly interesting matrix multiply because it's always just matching on one column and throwing that in there. But again, if you're ever looking at code, you're going to see that there is going to be this vocabulary table, and it is going to use matrix multiply in order to transform a whole list of tokens into numeric input all in one fell swoop. All right, so we've got most of the building blocks. Now let's just talk a little bit about the actual language models people build. So there's three architectures you're going to hear about: the encoder architecture, the decoder only architecture, and then the original attention is all you need paper was an encoder decoder architecture. So common examples, BERT and all of its children you'll hear about. That's an encoder only model. GPT-3, Llama, most of the LLMs in the news today are decoder only. And then for some translation things, you'll see the encoder decoder model. Is that a question? Yeah, we're close to the end. The book actually just came out a couple months ago, so this is all pretty much brand new material. I've supplemented this with some of my own, so this is all original content. Okay, so once again, here is the original transformer, okay, from the Attention is All You Need paper. On the left, this is the part we call the encoder. All right, in the Attention is All You Need paper, what happens is this thing runs on all the words, and then at the very tippy top, this line says, we've encoded some sort of dense information about each word, and then the decoder, we're going to pass that to. And so the right-hand half is the decoder. If you hear about an encoder-only model, okay, then what that means is we completely get rid of the right half and we only have the left half. What I've done on the right is I've redrawn this, getting rid of the parts that we don't keep, okay? And so what you'll see is pink is where your vocabulary gets turned into a length 512 vector. Orange is the attention. Blue is the MLP. And then we have a purple box where we convert it back to a vocabulary word, and the softmax just scales and chooses the word. In the decoder only model, what we're going to do is we're going to get rid of the left half. Okay, so we're going to get rid of this left half, but this box in the middle here is where we took the input coming from the encoder and we use that. So we can't do that because we don't have any input from the encoder. So this is the decoder only model. All right, and so you have a pink box where you do your embedding, attention, blue box for your fully connected, purple box where you turn it back, where we're going to get our logits, and then the softmax lets us pick which word. What I'm going to do now is I'm going to show you the encoder only and the decoder only side by side. I don't think I've ever seen this like in a textbook or in a presentation or anything like this. So you have the left and the right. And aside from the spacing and the fact that like some things are a mirror image or whatever, these are identical. So I just want to caution you that like you will hear people talk about decoder only and encoder only transformers. Architecturally, they're identical. What's different about it is how they're used. Okay? And it makes sense if you understand that the original attention paper was for translation. So he was like translating from English to French. Okay? And it made sense to call the first part the encoder because it was taking each word, it was encoding it in some information, And then the decoder was the part that was spitting out the French. Okay. But the names are, in my opinion, are a little bit of a misnomer at this point because neither of them is really encoding and neither of them is really decoding. And oh, by the way, they're identical. Okay. So a couple slides more, we're almost done. But what you'll see is that really, I'm not going to go super into depth, but what makes the encoders different is how they're used. So you put in some inputs, it gives you some outputs, and what's the loss function that you calculate on? Okay, that's what makes it an encoder model. I don't know if that's helpful or harmful, but at least like I felt like I should say something because it's kind of misleading to be talking about them as like such completely different things when it's like no, like if you just look at the diagram, there are some technical differences, but they're pretty small. All right. So here is the book picture for an encoder, a BERT model. Once again, this one is inputs on the left as opposed to the top or the bottom. So imagine that you've got a tension layer and you've got your feed forward. You're going to repeat this however many times, how many layers you have, K layers. Okay. But what you've done here is on your input, every so often, like about 1 out of every 6 words, you just completely deleted the word and you replaced it with this special token that says, I have masked out, I have deleted this word. Then when you train it, only on the places where you deleted a word, you tell the model, hey, can you predict what word I masked out? Okay. Shockingly, when you mask out words, they call this masked language modeling. It's really huge leap to understand how they came up with that name. Masked language modeling, it kind of makes sense why this would be one of the first models that people created because essentially you're just using this architecture. Again, this is encoder only, so it's only the left half. You're using it kind of vanilla. And what was really creative about this is when you do supervised learning, what's the hardest part about supervised learning? Generally speaking, getting the labels, getting the labeled data. It's the problem, right? So I'm trying to train a language model. How do I get labeled data? If I have a sentence that the train pulled into the station, whatever, what output am I going to have the model put out that I'm going to grade it on, whether it was correct or is incorrect, right? So for images, you say, this is a dog, this is a cat. I have class labels. Somebody still has to like label all these images to say whether it's a dog or a cat or whatever. But it's like not really clear with language how you do that. So the brilliant thing from the BERT paper is we're going to turn this into a self-supervised problem. And you now see this all over the place in advanced machine learning. I'm going to find a domain where I have a lot of data. And because labeling is too expensive, I'm actually going to remove information that I have and make that the thing that the model needs to predict what I removed, because labeling is so expensive. But removing, you can automate. So if I have an image and I just cut out a square that's 16 by 16 and have it be a black hole in the middle, I can tell the model, predict what used to be in that 16 by 16 square, and I don't need to pay any people to do labeling. So this was really a bit of a watershed moment in terms of showing us on a large scale, you can remove things in order to create your sort of self-labeled data. And now you can just scrape the internet for sentences and start training the thing. And at that time, we thought, oh, we train it on all of Wikipedia. That was big. Back then, we thought that was huge. Little did we know. So that's what the BERT model looks like. And today, if you hear about an encoder-only model, it's really the idea that at every position, the model is predicting sort of something about the word, and for the masked out words, that's what it's predicting. You'll notice also there's this very special non-word token, the CLS at the beginning, and that gets used in these models. So this also introduces us to the idea that you're now going to pre-train the model on general language, and then maybe you're going to fine-tune it for your particular task. So common thing, one of the very first things we saw was sentiment prediction, positive, negative. Okay, so what you do is you run your text through this model, and it's going to do its thing. You no longer have mass tokens, so it no longer needs to worry about that. You're going to actually give it all the words now that you're, in production mode. But what you do is you just put a little prediction head on this first token. The CLS is what they call the classification token. And so what the model is going to do is, even though it has n outputs for every single word, you're going to ignore all but the first. So those were useful for training it to get it to understand language. You're not actually going to use them. Instead, you're only going to use the output from the 0th token, and you're going to run that through a prediction head just to say, 1 or 0, positive or negative, or 1 or -1. A different way that you can train this model is you can say, I want to have some kind of embeddings that this model outputs. And so in that case, now you really are going to use the outputs from each word. But what we're talking about here is, you may say, wait a second, what do you mean word embeddings? I already embedded words. That was the very first thing I did. In this case, Zara works at Chanel in Victoria. Wow, that's a funny sentence. Okay. So the word works is just this fixed embedding we have for the word works. The output of this model is going to be a vector that is specific to works in the full sentence. Zara works at Chanel in Victoria, blah, 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 blah. So it's now, instead of a fixed embedding for the word, it is a context aware embedding for the word. And there's other ways that people use BERT models, and whatever, entity recognition, all sorts of things. But so the training on this is what you can see, where you have one word coming, for every word coming in, you've got an output coming out that you're paying attention to. Is Gemini decoder only or encoder only? Gemini is a decoder only model. All right. This is, okay, so now we're gonna talk about decoder only models, and they get used very differently. So in this case, you can see you have the input, the fish lived in the, okay? And let's say the model predicts a bunch of different words, and for whatever reason, we chose the word blue as the next token. It's not actually the max, but you don't have to choose the max. So then you say, oh, okay, if the next word is blue, then I'm going to input the fish lived in the blue and see what it thinks the next token is going to be. And then we're going to choose C, okay? So in this case, this is now a generative model, okay, where we're outputting one word at a time. And so we're using the model differently, even though the architecture is the same. So a little bit more about that. You'll hear people talk about it's an autoregressive model, and basically the way it works is, given the first few words, I don't even remember what it was, the fish lived in the, okay, I'm going to say, what is the most probable word that comes next based on the previous words being the fish lived in the, if you know your probability, your conditional probability formulation. For this sentence, it takes great personal courage, blah, 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 to predict the next word. What you can do is you can, treating them as independent, you can take the probability of the first word being it, the probability that the next word is takes, given that the first word was it, then the conditional probability, so on and so forth. If you write this out mathematically, you get this this multiplication, this product in pi notation. Not super important, but just to understand, when people talk about something being autoregressive, basically what it means is that everything depends on the things that came before it. So it's not very common, not very popular, but there were autoregressive image generation models where it would output the pixel in the upper left corner. And based on that, it would predict the pixel that's next to it. And it would keep doing this until it got to the top row. And then it would say, okay, now I'm going to predict the first pixel on the second row. And it would do that. And it would autoregressively predict the image one pixel at a time. So this is the diagram on the slides. You'll notice it's the same diagram, right? So in this case, what we're doing is we're really going to care about the output for the last token. So the fish lived in, what is the word that comes after in. We're going to kind of ignore the rest of them. Okay. So here we go. The fish lived in the, and we're going to predict this. If you're clever, what you can realize is that while we're training the model does have outputs for every single word. So even though we only care about the last one, we can read out what it predicted would come after the word the. We can read out what it predicted the word would be after fish. And so what we can actually do is we can say, when we're training the model, we can calculate loss over all the predictions all at once. And so this particular hack is the reason why Gemini, GPT-3, GPT-4, Llama, Mistral, all of these are decoder-only models, is because this hack allows you, if you have a context length 4,000, to get 4,000 inputs, 4,000 losses simultaneously. It's one set of weights that's shared across all the positions. So in one pass, you're getting 4,000 backpropagation inputs to how to update your weights. So you don't get that if you do the BERT style thing. If you're masking 1/6 of the words, then maybe at most 1/6 of the positions are giving you any feedback. I don't know if I can say this like authoritatively, but the bottom line is it is convenient and fast to train this style of decoder only model. And from what I've read, I don't know if anybody has any other information, but like they really, really want to take advantage of this business of if it's length 4,000, I'm going to get 4,000 input signals. So when you have this large corpus and you're like scraping, let's say, Wikipedia off the internet, you say, okay, article number 1, I'm going to take the first 4,000 tokens, I'm going to pass it into my model, and I'm going to calculate the loss and run, backprop. Next 4,000, next 4,000. What do you do when you get to the end of a Wikipedia article? Okay, if the end of the Wikipedia article only has 2,000 words, so that it's only half full, they will not waste those last 2,000. What they'll do is they'll just take the first 2,000 words from the next article, jam them in there, even though they have absolutely nothing to do with the previous 2,000 words. The downside of having words that don't connect to each other, don't mean anything, are outweighed by the fact that they're getting so much more training signal by always having this. So when I first saw this, I thought it was kind of odd, but that's actually why people love these decoder-only models, is because when they train them, they always train it on a fully packed batch. It's always max length. They never, ever, ever waste any of those positions that aren't going to send any backprop signal for the training. All right, so that was a diagram in the slides. This is a diagram in the book, similar thing. And again, the idea is that at every position, we're making a prediction, but the loss calculation is different than what we saw in the BERT model. In the BERT model, we were predicting for the current position, what was the word that I hid from you? In this case, you're saying predict the next word. And in order to do that, you need to prevent the model from cheating, because it's like, wait, you just gave me all the words. If you want me to predict the next word, I can just look down one row and I can see that's the word. So there's this extra thing that's added. I think I timed it so it's the right. No, it's not. Okay, but so there's the attention is masked, so that basically, and at any given word, it can only look at the words that came before it. It can't look at the words that came after it. Otherwise, the model would cheat and it wouldn't relearn anything. And so when you do this, then you force the model to actually say, when you get to great, you've only seen 3 words, predict what the next word is going to be, and you can't just cheat and look down and see courage, because they've masked out all of those. So this is a diagram in the book. I wanted to take a moment. This is the diagram that I promised you before. So I showed you before the attention diagram. This is me having done a whole bunch of copy and paste on the attention diagram. The pink box is still at the bottom, okay? And the purple box is still at the top. But now what I've done is just copy and pasted the orange and blue attention and feed forward layers. So orange, blue layer 2, orange, blue layer 3, repeat, repeat, repeat until you have your final one. Also, if you have 4,000 tokens, what does it look like? Well, then you're going to make 4,000 copies of it horizontally, okay? Now, these copies are truly Siamese twins, or no, not even identical twins. The weights for each of these token positions are identical, and when you're doing training, they all change together, okay? This is not 4,000 separate things. It's just, which is why in the original diagram, they don't show it, because there really is only one set of weights. But mentally, if you're wondering, how do I process text? Mentally, you can think of it as having 4,000 across here. You pass in 4,000 different words, each of which is embedded by the pink thing separately. And then you do this calculation on all of them, and then the output of the first layer is the exact same dimensionality as its input. So the nice thing about this is you can stack layers, and you can change the number of layers, and the dimensionality never changes. If you look at a CNN, after you've gone through the CNN a certain while, the size of your image shrinks and the number of channels grows. So you can't just sort of say, I'm just going to have an arbitrary number of these layers. But by having this particular architecture, you're like, yeah, let's try 12 because I think I can compute this in a week or whatever, train this in a week. And then if it starts to work well, you're like, oh, maybe I'll try 24 of them and I'll ask for enough budget to train this for, a month. And that works really well. You're like, let's build the extra large version of my GPT model, and I'm going to ask for a budget enough compute that I don't want to wait, 6 months to train it. So instead, what I'm going to do is I'm going to ask for cluster, and so I'm going to have 8 GPUs, and now I only have to wait 3 weeks to train it or whatever. So that's very convenient for being able to like size things up and down. The other comment that I want to make, so the one time that this residual idea is important is in this diagram, I've changed it where it used to be the orange and the blue boxes were sort of in the middle, and you had to look closely to see that there was a residual line that went around them, okay? In this case, I've moved them to side and kept the residual line in the straight part. And so I happen to be particularly interested in interpretability research, so I read a lot of stuff on like LLM interpretability. And so the way that scientists now, the conventional wisdom, the way they talk about this is imagine that you do your original embedding, you've got a length 512 vector. It is going to pass through unchanged all the way until the next token prediction, the output, unless somebody modifies it. So the idea is these individual layers, the attention and the feed forward, the orange and the blue boxes, their idea is as this data passes through, they're gonna like twist it, shape it, squeeze it, pull it, and they're gonna modify it a little bit at a time until by the end it gets modified enough that the model's able to say, with all of those additions, I can now predict that the next token will be whatever. You actually can, you can build a 0-layer language model. It works. What it means, though, is that for any given word, like boy, the next word that's predicted will always be identical because there's no layers to twist and shape it. But you can actually build one, and if you train it, it actually works pretty decently. What it basically is, if you're familiar with NLP, is it's a bigram model. It just says for every word, what is the most probable next word that's going to follow it, okay? But conceptually, that's the mental model that people have right now, is that imagine that this is a bigram model with just the pink and the purple boxes, and it's the job of all the layers in between to pull information, twist whatever, in order to supplement what we know from basic bigram statistics in order to now have this be a much smarter thing. And the attention layers, because they're allowed to look to the left at all the words that came before, if trained well, they can do very smart things to say, oh, I'm on the word there. This probably is referring to the word restaurant. I need to take certain information about restaurants and copy it. And so that's where literally in this residual stream, I don't know, it's a bit of an eye chart, but where all these outputs are, there's a little plus in a circle there. So what every layer is doing is they're literally just writing, they're just adding numbers onto the residual stream. You can add negative numbers, okay? So you can actually erase things, because if you read on the residual stream, there's a 10, and you write a negative 10, you're basically erasing. So you do see that behavior in language models where sometimes there'll be something that comes in and it just gets erased. It gets turned into close to zeros so that you now have scratch space for something else to write into that spot, okay? But essentially that's what they're doing is They're reading information off the residual stream. The feed-forward layers can write stuff back to that residual stream. The attention layers can copy information from other token positions, and they can write that into the current residual stream. So it's not completely known how it works, but for the earlier discussion, it really is about, I'm going to go and pay attention to the word restaurant. I'm going to copy the value information from restaurant and write it into the residual stream in my current token position so that the layers above me can basically act as if the word restaurant were here to a certain extent. All right. And so finally, encoder decoder. I haven't really heard much about this, but the original transformer model, it was a translation thing. And so the encoder, it did create a bunch of information about the English text. And then basically the decoder was writing French, and it was able to take this. So it's included in the book. It's probably important for historical reasons, but T5, I think, is an encoder decoder model. That's about the only well-known model I can think of that's like encoder decoder. The key thing here is that for language models, we've talked about these architectures. It's really the self-attention mechanism. When people say transformers have taken over machine learning and they're now in vision and they're now in whatever, well, the reality is this transformer that has like the self-attention and the MLP and the residual stream, that's not what people are necessarily using. What they're using is self-attention. So it's a little bit of a misnomer. Self-attention, well, not even self-attention, dot product attention has taken over machine learning. We just say transformers because it appeared in the transformer paper, but it's not technically using a transformer. All right, let me just check to see if there's questions. Yeah, so question. So I showed that the encoder and decoder are architecturally the same. This is the type of training task that distinguishes them. Yes, it's the training task and the loss function that you use. In order to do next token prediction, in order to prevent the model from cheating, you do also need to add a mask to the attention so that you can only look at words that came before you, that came after you. But ultimately, when you hear people talk about encoder and decoder, I feel like they're kind of explaining it wrong because they really are the same. All right, so there's a million things we could talk about language models. I can't remember if there's, oh, there's a couple more slides here. I think we're running late. I'm not looking at the time. So I'm kind of wrap things up here. But just know that the chapter also talks about it's a problem when you get really long text because it gets expensive to compare this token to every other token that came before it. So if there's 4,000, then you need to compare to 4,000 of them. When you go to 16,000, now you need to do 16,000 comparisons. And now that people are trying to go to 100,000, that's 100,000 tokens being compared to 999,000 other tokens each. It's growing quadratically. So there's some schemes that people have used. If you're curious, it's kind of good to know. By the way, none of these schemes really work that great, so probably not super important. And then the other thing is that transformers are now being used for other things that we talked about. So specifically, they show two image models. So there's the original vision transformer, VIT, and then there's Swin transformer. What I think is the important thing to know is people have now learned that if you wanted to take an image and have every pixel be an input, 1,000 by 1,000 image would have a million pixels, and if it's 3 colors, you'd have 3 million inputs. That's a super, super long transformer. People tried various things. Ultimately, what somebody says, well, what if I just take a patch of 16 by 16 pixels and I have that be one token? And it's really not a problem because tokens kept getting bigger. I said 512, but the standard token these days is probably 10,000 or so. Okay. You don't need 10,000 dimensions to represent one pixel. Okay. So you can afford to say, I'm going to have 256 3-color pixels represented by a length 10,000 vector without losing much information. That worked. VIT is a very expensive compute model, but at the time that it came out, it basically went to the top of a lot of computer vision leaderboards for various tasks. and there's been like slight improvements. There's a debate as to like, are CNNs better? Are transformers better for vision? Part of it depends on how well you train it and some tricks that you apply. It's not clear, but what is clear is that whether you want to or not, you can train a transformer to be approximately as good or better than a CNN, okay? And the lesson from that is you can actually train a transformer to be as good as any other architecture for any modality, for audio, for speech, for video, for 3D protein configurations. There's two ingredients that you need. One, you need massive amounts of data, okay? The fact that the transformer is so general purpose that it can learn any pattern means you need a lot of examples to show it what the pattern is, because it'll represent anything. It has no inductive bias, okay? So what you'll see is where people have breakthrough transformer-based models is where they have some massive amount of data, or where they're able to generate and say, I'm going to synthetically. So if Tesla's going to do self-driving, they need 8 trillion hours of driving video in order to train their models, okay? The other ingredient that you need, not necessarily quite as hard, but it's not always obvious, is you need to figure out how I'm going to convert my input into tokens such that I have in the ballpark of a few thousand tokens. Okay, so what people have learned is if you can tokenize it, doesn't matter what it is, chemistry, biology, astronomy, speech, if you can figure out how to tokenize it, give it transformer data and it'll get you to state-of-the-art performance. So I'm not going to get into the debate of should you use a transformer. It might be more expensive. It might be better to have a different model, okay? But somebody will be able to train a transformer with enough data to equal the performance of whatever your other model is. And so if you don't have another model, then the good news is any problem you want to solve, if you can find yourself enough data, then you can train a transformer and it will solve it. So, you know, you want to whatever, I don't know, teach it to speak Klingon, it'll do it. All right, let's check on the chat. Yep, okay, cool. So we're gonna wrap things here. Once again, still working out the logistics for hybrid, so thanks for everybody for putting up with everything. So I will stop the recording here, and people who are here physically, if people want to hang out a little bit longer, we can do that. I'll stay on the Zoom for a couple minutes just to see if there's any last questions. Okay, yeah, please.
I experience a lot of failures in terms of how inaccurate it is for all the labeling images, as opposed to using some traditional computer vision methods for labeling. But so I wonder, like, where can I start troubleshooting to increase the performance if we do want to build this connection between images and
yeah. So the question is about just paraphrasing, just the nugget of it. Using a model to label images. So the first thing I would say is that I don't know if you're using transfer learning, but you know you're probably much better off starting off with a pre-trained model. Okay, and so then yeah, probably maybe a offline conversation about some different ideas. But yes, amount of data is often a problem with transformer models because they're big and they do tend to need a lot of data in order to understand what it is that you're trying to fine tune in. Whatever you're going to train it on. So in this case, it would be like image and your correct labels for what you want the model to output for those. So it depends on the use case. So so in general, with a transformer model, initial training, you need internet scale gobs of data. You need something that's in the billions or trillions. For fine tuning, generic transformer models, you tend to need a lot of data. There's an exception with language models, which kind of gets into this unique place that we're at. So language models like ChatGPT, they have this phenomenon of what we call in-context learning, okay? So in addition to just general language and understanding, they actually can understand sort of instructions and patterns from the earlier part of the text that you have, okay? So it turns out that you can fine-tune language models like GPT, Chat GPT or whatever, on a fairly small amount of data. Like I've seen people train it on like 50 examples, okay? But that is a unique case taking advantage of the fact that the models have this sort of extra ability to not only use the fine-tuning that you did, but the special instructions you give it in the prompt for what you want it to do, okay? If you don't have that ability to give it a special prompt, then you tend to need a lot of data to train.
Like for me, it might seem like exactly the same, but like the model might react very dramatically to the differences of words you choose to use.
Oh, that's interesting.
So still trying to figure out like how to resolve like the problem of what is a good prompt and what is it that, even though it looks the same to me sometimes, but the word choice dramatically affect the results. But we can talk about
Yeah. So you're saying that the word choice affects the results. Are you talking about the word choice on your prompt or the word choice on your labels? Word choice on your prompt. Yeah. So yeah, we can talk about that, and then maybe talk to Ryan, because I think he may have a solution for you using prompt tuning. All right, so I'm going to wrap things up here. Thanks everybody for joining in person. Thanks everybody for joining us online.